as they presented earlier. So let's start the presentation.
I hope you can see my screen.
Yes.
Okay, perfect. So the team name has a long story. I'm not going to explain it, but the EXE means external. So all data are external. Okay. So hello everyone. I'm Bolio. I'm part of the three-person team that got the third place in the retrieval and fourth place in the recognition. And since like most teams, the two solutions share a lot of things, the host asked me to present it together. So a little bit of background. So my teammate Qishan and me, we were also part of the third place competition last year in the recognition. And that was a four-person team. And last year we had more time. The competition lasted longer, so we did more experiment, and we developed a pretty strong pipeline, which we reused. We largely reused the pipeline this year. So here is the overview of that pipeline. I think the most important thing is we introduced a sub-center arc-face with dynamic margins. It's an improvement over the regular arc-face to tackle the extreme imbalance of this Google landmark dataset. And it's proven to be very effective. And in fact, I think it's used by many teams this year. And our pipeline also used the progressive training with increasing image size. For the pre-trained models, we use the indispensable library called team library, the PyTorch image model, which is very popular these days. And for other things like augmentation and training schedule and stuff, we just reused the same thing as last year. In terms of the model's backbone, so last year we mostly used EfficientNet at a different level because EfficientNet was kind of state of the art last year. But since then, there are quite a few new models being introduced, like EfficientNet V2 and NFNet, and more importantly, the vision transformers. So what we did this year is to replace the EfficientNet backbone from last year by the newer model architecture, and loaded the pre-trained model in the team library and trained it as the same way. Now here is the retrievals ensemble. So in the retrieval ensemble, there are 7 models. So there are 3 transformers, all use the image size of 384. This is because in the team library, the biggest pre-trained model has this image size, and it's not as easy to go to bigger image size. And there are also 2 new CNN and 2 old CNN. For the two old CNN, we basically took the weights from last year and fine-tuned for a few epochs so that we didn't have to start from scratch. And the interesting thing is that for the transformers, for the swing large and the VIT large, they have slightly lower local recognition support than their CNN counterpart, but they have significantly higher local retrieval support than the CNNs. We think that is because transformers are patch-based, and so they can capture more of the local features, if you will, and the attention can make the model better at capture the like the relationship between different part of the local features on the image. So the recognition ensemble, on the other hand, have 11 models. So the same 3 transformers, but this one has 4 more CNNs, mostly from fine-tuning last year's models. We also try to add these 4 CNNs into the retrieval ensemble, but it reduces the support. We think it's because the transformers are so important for the retrieval. Adding more CNNs would reduce the relative importance of the transformers in the retrieval ensemble. But they did improve the recognition ensemble. That's why the recognition ensemble has more models. And finally, is the post-processing, which is been proven to be very effective for both the GAP metric and the MAP metric. All the top teams in previous years used post-processing to improve those metrics. So we did as well. For the retrieval, our post-processing was inspired by the winner 2 years ago. So what they did is start from percent similarity, but then move all the positive matches to before all the negative matches. So we improved upon that because we think those adjustments are like hard adjustment. They just move all the positive to all before all the negatives, regardless of other factors. What we did is a softer adjustment to give a boost or a penalty adjustment, depending on whether they are the same, whether the query and the index are the same class, but also depending on how confident they are, basically the probability of those predictions. So the result is better. For the recognition, what we did is basically combine the post-processing of all the top 3 teams from last year, including our team. For the recognition, the post-processing, the most important thing is because there are a lot of non-landmark distractors, so the important thing is to reduce the probability if your test image is matched with a non-landmark image distractor. So that is our solutions. Okay. I can answer questions later.
Okay, thank you.
Yeah.
All right. As I mentioned earlier, we're going to have a combined Q&A session after 3 talks. Okay. It seems that the Zhang Wesley team is ready for presentation. So can you start now?
Okay, can you see my screen?
Yes.
Okay. I'll show our second place solution to Google Landmark Retrieval. And I'm from Alibaba Dharma Academy. And I will first introduce person re-identification to landmark retrieval. And for person re-identification, we just do person detection, and the images are cropped. And this is a fine-grained retrieval. For example, different person for different ID. And the color is very important for this case. For example, the man with purple clothes. And for landmark retrieval, however, the landmarks are uncropped. And we see there is some alignment problems. Also, beyond color, shape, and texture is also very important for this case. And for our solutions, we learn from previous top solutions for the 2020 and 2019, and that is we gradually enlarge input size and the data scale, and we use strong backbones and some strong loss functions like ArcFace. And I will introduce some new contributions. The first one is bag of tricks from person re-identification. And next is continent-aware sampling strategy. And next is landmark country-aware re-ranking. First, bag of tricks from person ID. There are many tricks in person re-identification. For example, random erasing here. For when training our networks, we just put some black patches on the images, and this is a data augmentation, and this proves to be very useful for person re-identification and some classification problems. So we use this, and some and label smoothing. We just use some soft logic for training, and the triplet loss. It is very common metric learning loss function, and some IBN extension. This is for backbone, and we use last thread as one, so to use a larger input. And during our findings, during our experiments, we find that random erasing is very useful. However, for label smoothing, which is useful in person re-identification, it fails for landmark retrieval, especially for ArcFace. We think we should skip this. We should skip this for landmark retrieval. And for continent-aware sampling strategy, as the towards a fairer landmark recognition dataset said, this year's competition has fairer ratios for landmarks, and we think Asia data should be more important. So we in an epoch we sample more data. We sample more Asia data And for data, we favor clean data, and noisy data we set low probability. And we list the experiments. ID uniform means we treat every ID equally, and this favors many long-tailed data with few images. And this is very useful in face recognition and person identification. But in this long-tailed data set, Google Landmark V2, it is harmful. And for softmax, it is commonly used in previous solutions, and it performs very well. And for the continent-aware sampling, we favor some Asia data, and it performs better on the data set, on the evaluation. And some landmark and some re-ranking method. We use query soft voting of landmark and country from GLD v2. That is, if a query has, we use soft voting for the landmark and the country tag. For the country tag, we get it from the GLD v2 official set. We enhance index images with the same landmark and the same country as the query. For example, here we can see the example here. The query image is Jiangsu Chenghuang Miao, and we have the original rank list here. And here we can see the raw prediction for the landmark tag is Jiangsu Chenghuang Miao and China. And here the next one is serial template in India, and we use this the first landmark tag to pull to add to upvote the same landmark as the query. And so next we can see we upvote the we upvote the images with the same landmarks to the query. And also, for example, this false negative, it also shares the same shares a similar appearance, but however, it has a different country. So we just give it no. We give no re-ranking scores for that. And at last, we can see we pull over landmarks. We pull images with the same landmarks, also the same country, and we think the re-ranking method is very useful in our experiments. And next, we show our results on the leaderboard. We rank the second at the private leaderboard. And thank you for the presentation.
All right, thanks for the talk. Next, the third presenter, the underfeeding. So underfeeding is the fifth place team in the Retrieval challenge.
Okay. Take a moment, please. Can you see my presentation?
Yes.
Okay. So, hello everyone. Thank you for giving us such an opportunity in ICCV workshop. Let's start presentation of our fifth place solution from Hiroki Yamamoto and Kuba Shafan. First, I will talk about overview, training. Then Kuma, I will explain about our possible session. First, I will talk about our overview. As I will the top of our solution diagram. We use 5 models, which are efficient to V2, 2 V2Ms, and V2XL. These models extract vectors from new index and new test set in the Kaggle notebook. Each model has a score about 0.38 to 0.40 when we use simple KNN using cosine similarity as its distance. Then, after we concatenate all vectors, it achieves a public score 0.42486 and 0.43425. And finally, we use the breached confidence and for post-processing with embedding vectors that are pre-computed in our local machine. And with training data, we achieve public 0.49686 private 0.525, which is fifth place score in Retrieval track. And let's move on to training. I explain about training details. Model structure is based on efficient V2 backbones and arc-based here in the here. And we use global average pruning, dropout, and dense layers between efficient V2 backbone and arc-based. We search index images using 520 vector, which is output from dense layer with its output applied to it. We use GLD with 41 million, 4.1 million as a training dataset. Our optimizer is ADA, and our schedule is cosine annealing. We trained for 15 epochs. We also bigger batch size proved better than smaller batch size. So we use gradient accumulation and mixed pressure for keeping bigger batch size. We use the batch size of 128 to 256 batch size. In this competition, our team used TPU V3 8 cores in GCP and TPU Research Cloud program by Google. It's a great program and helped our first experiments. With thanks to TPU Research Cloud program, it's helped training bigger image size and faster training. On test and index image inferences, we use horizontal flip for test time data augmentation. Finally, we concatenate all models vectors used for post-processing. That's all about overview and training from Hiroki Yamamoto. Now I will pass on Kumar Sharma for explanation about post-processing.
Yeah, hello everyone. So I am Kumar Shubham from India. I graduated from IIT Delhi summer 2020. Right now I am working as a machine learning engineer at Savan Media Private Limited, also known as Geo Savan. So I am actively participating in Kaggle competitions for a year now, and I am actively participating in Kaggle competitions for a year now, and this has been one of the most successful competitions in my short Kaggle journey. So I am going to describe the post-processing part of our fifth place solution. So our post-processing is based on what we call bridged connections. So many a time we can't match two images belonging to same landmark directly using KNN. For example, take indoor and outdoor images of the same building, or say front or back of the same building here. So establishing such a connection with cosine distances between 512 dimension embedding vector trained just with visual features is difficult. So we try to establish these connections using ground truth data given to us, as most winning solution did. So couple of things before we go forward. So I will use the term reference image. So this refers to both index as well as test image. So we use rapids for all the nearest neighbor search steps because it gives better performance in terms of search time with the use of GPUs. We will use the terms confidence or similarity interchangeably here. So by confidence, we mean how much are we confident that two images belong to the same landmark here. So now coming to the approach. So first, for every reference image, we search for top 300 neighbors from train set. So this is our candidate set. So we use non-landmark penalization to penalize train images with significant non-landmark fractions, such as cars, people. So for non-landmark penalization, we compute non-landmark scores for each train image with the help of non-landmark images from GLD-V2 2019 test set. For each train image, we simply take 10 nearest neighbor from non-landmark set and average their distance. So this is similar to the first place recognition solution. Yeah. So then for each reference image, we try to find possible landmarks. So we find the distance between landmark and reference image, which we compute taking the top two nearest train images belonging to landmark and averaging their distance. Then we just pick the top 5 landmarks for each reference image, that is each test as well as index. We converted all distances into confidence or similarity using confidence equal to 1 minus distance. So in most of the cases, first landmark was correct. So we tried to leverage this by adding 0.5 confidence bonus to most confident landmark for each index and test set. So now we compute the Bridget confidence between test and index set using the distances calculated above. So for each test and index image, we find all the landmarks they have in common. So these landmarks kind of act like bridges between the test and index landmarks, the test and index images. So we define similarity between test and index images using a particular landmark as a bridge as minimum of similarity between test and landmark and similarity between test index as minimum of similarity between test and landmark and similarity between index and landmark. We define Bridget connection as maximum of these similarity values for all possible landmarks. So similarly, we get Bridget connections for all test index pairs from our candidate set. So then we move to direct distance computation part. So there we use database augmentation on test and index embedding. We improve the quality of image representation by leveraging the features of their neighbor. We aggregated the embedding of nearest k neighbors. K in our case was 2. The sum is weighted depending on the rank of neighbor with weight is equal to k minus r upon k, where r is the rank of the neighbor and k is the total number of considered neighbors. Then we search for 100 nearest neighbors with these refined embeddings using cosine similarity. Yeah. So with this, we call this cosine similarity as direct confidence. Next, we aggregate the direct and Bridget confidence using simple power averaging approach. So power 3 worked best for us. So confidence to the power 3 plus Bridget confidence to the power 3. This post processing gave a boost around 0.09 for our mean average precision metric for a single model and 0.075 for our final ensemble. So this concludes our summary for fifth place solution to Google Landmark Retrieval Challenge. Yeah. So thank you for listening to us. We are open to questions.
Right. Thanks all presenters. Is there any questions to the winner teams? Well, I have a question to John Wesley team. So you mentioned that your idea is from the person re-ID the tasks. So can you explain what's the main difference between the person re-ID problem and this retrieval problem? So what's the main challenge to the transfer the existing technique in the person re-ID to the image retriever task?
Okay, can I share my desktop again?
Yeah, sure.
Okay. I think the main difference is detection. First of all, for person ID, the images of the person are detected, and for landmark retrieval, we can see some landmarks. There are some background, and the landmarks is not in the center or not very salient. And for person ID, it has already been detected. Also, the color information for person ID, the color is very, very important about 70% or 80% important. And I think for landmark retrieval color, for example, the Golden State or some other buildings, it is rigid, and some local matching method seems to be important. And these buildings, so some color information seems not very important, but the shape or texture seems important. And I think the main difference is first detection, and the next is color information.
Okay, thanks. Any other question to the presenters? Yeah, actually, I have another question. The question to the underfeeding team. I wonder if you have any, intuition about the equation for the final confidence. The in the slide at the lower right corner of the slide, there was the equation for the confidence. So do you have any intuition to make that equation?
So the power averaging approach we took from last year's recognition third place solution. So after it worked, we thought about why it works. So what we saw was when we were analyzing the results of direct confidence and rigid connections. So we saw that both of these both the direct as well as rigid connections have very high precision at higher confidence levels. But as we go downward, so the precision falls rapidly. So using power 3 here aims to increase the relative gap between the confidence values.
Okay, I see. Yeah. Okay. Thank you so much. And it seems that sorry. It seems that there's no other questions to the presenters. I thanks again to the presenters, and let me conclude the session.
All right, thanks everyone. Thanks, William, for hosting the session. So